Good morning, everybody. My name is Felice Alberto Sfregola, and I'm a PhD candidate in physics in the University of Bari, Aldo Moro, in Italy. And today I will present to you our work about improving the efficiency in acoustophoretic particle sorting microfluidic devices using a fully coupled numerical model based on finite element analysis. The model was fully characterized and validated through experiments. Nowadays, the analysis of biological and environmental samples is of utmost importance for our health and security. However, these suspensions are usually very complex and the relevant information is carried by specific and rare components, also called biomarkers, for example, circulating tumor cells in whole blood. For this reason, improving the sorting efficiency of these devices is essential for reliable diagnostics and analysis. Several strategies are available. For example, passive techniques rely on the channel geometry to leverage hydrodynamic properties of particles in order to have a simple way to sort them according to their size. However, in this way, it is possible only to have a limited control and selectivity over the process. For this reason, it's more interesting to employ active field to finally control the particle motion. For example, in the electrophoresis and magnetophoresis, it's required for the particles to have an electric or magnetic field. In our case, with acoustophoresis, it is possible to use acoustic fields to manipulate particles in a contactless and label-free manner, since the property that we are leveraging is given by the size and the density, as we will see later, of particles. This is possible generating surface acoustic waves on the surface of piezoelectric substrates using interdigital transducers, also called IDTs. When two surface acoustic waves are propagating in a counter way, the interference can generate a standing surface acoustic wave field. Then this field can be coupled with a liquid flowing within a microfluidic channel, and thus on the particles flowing within, the pressure gradients will give an acoustic radiation force. The balance of this acoustic radiation force with the drag force given by the flow itself gives out the particle trajectories. Now let's have a look at the analytical expressions of these forces. For the acoustic radiation force, first of all, we can see a dependence on the volume of the particle. For a spherical particle, this is given by the third power of the radius, so there is a strong dependence on this parameter. Then we have the acoustic energy, which depends, of course, on the driving voltage. And finally, the material properties of the particles. On the other hand, the hydrodynamic drag forces depends for spherical particles on the particle radius, so in a linear way, in a weaker way, we can say. Then we have the particle velocity, which is given by the flow rate, and finally the fluid viscosity. We will assume that the particles are made of polystyrene, while the fluid is simple water. As you can see, the parameters are strongly coupled, and for this reason it's not possible to forecast the particle trajectories in an analytic way. At the same time, it's not possible to employ simplified or bidimensional model to study this complex 3D nature problem. For this reason, until now, the optimization of this kind of devices is given by trial and error approaches. And for this reason, we propose, our goal is to develop and validate a fully coupled three-dimensional predictive numerical model in order to have a more straightforward, cheaper and faster way to optimize this kind of devices. For this study, the following real device was considered. A lithium niobate substrate of 500 micrometers was spattered on with an aluminum metallic film in order to produced two IDT pads with a pitch of 200 micrometers, corresponding to the wavelength of the generated surface acoustic waves. This corresponds to an operational frequency of 19.3 MHz. The microfluidic structure was then obtained in PDMS by mold replica processes, and the device was then assembled through oxygen plasma bonding. Here you can see the width and the depth of the channel fabricated. Both values are a multiple of the pitch and thus the wavelength of the SAW wave. This was done in order to have a correspondence between the periodicity of the wave and the channel itself. The real device was then reproduced in a 3D environment in COMSOL Multiphysics in order to have an actual digital twin. Two domains can be observed. The first one is the piezoelectric substrate and the IDTs, which corresponds to the electromechanical part of the problem. Then we have the fluidic, the CFD part of the problem with the microfluidic channel. Let's now have a look at the cross-section of the device. In order to replicate the real phenomenon, the following boundary conditions were applied to the geometry. On the bottom surface of the piezoelectric substrate, the vanishing displacement and potential fields was applied, while on the top surface, the stress-free boundary condition was employed. In order to allow the acoustic energy to flow from the piezoelectric substrate to the microfluidic channel, the acoustic boundary streaming coupling was applied at the interface between the microfluidic channel and the piezoelectric substrate. Regarding the meshing strategy, a free triangular mesh with a maximum element size of 1/6 of the pitch was applied on the top and bottom surface, and then a free tetrahedral in volume swipe was employed for the rest of the volume. Simulations were then performed in a sequential manner, with each step providing the input and starting values for the following one. The first step was to simulate the generation of the standing surface acoustic wave field, and that was done using the piezoelectric module. In this way, it was possible to obtain the actual displacement field on the top surface of the piezoelectric substrate. Then the microfluidic channel was placed on top of the substrate, and the coupling between the fluid and the structure was obtained through the fluid structure interaction module. In this way, it was possible to obtain the 3D acoustic pressure field within the microfluidic channel. Finally, the laminar flow was imposed within the channel in order to have the steady-state velocity field within the channel itself. Finally, all these results converged in the study of the particle trajectories using the particle tracing module. In this way, it was possible to study the balance between the two acting forces on the particles. Let's now discuss the results obtained through the simulations. The first step was the generation of the standing SAW field. This study was obtained at the resonant frequency of 19.3 MHz and at two different driving voltages of 2.5 and 10 volts. As you can see from the plot, a periodic displacement was observed on the top surface. Then the microfluidic channel was placed on top on the substrate, the piezoelectric substrate. And here you can see how the periodic pressure nodes and antinodes are also observable inside the microfluidic channel. The distribution of these pressure field defines the acoustic radiation force acting on the particles. In the third step, we can see the steady-state laminar flow computed at the two different flow rates of 500 and 100 microliter per minute. As you can see, and as expected, the profile of the velocity field is parabolic. And also in this case, the flow field defines the hydrodynamic drag force acting on particles. The last simulation step was to study the particle trajectories, and to this end, polystyrene particles were considered, with two different diameters, 6 and 20 micrometers, corresponding respectively to red blood cells and circulating tumor cells. Here in the plot, you can see in a black dashed line the reference trajectory obtained at zero input voltage. Increasing the input voltage increases the lateral deflection. On the other hand, increasing the value of the flow rate, the deflection decreases. This effect is even more evident for the 20 micrometer particles, showing that there is a strong dependence on the size. The model was then validated through the following experimental setup, under the same operating condition used in the simulations. The flow controller was used to impose the flow rate within the microfluidic channel at a value of 100 and 500 micrometer per second. The solution, the suspension used is made of deionized water and fluorescent polystyrene microspheres. The trajectories were then extracted through a fluorescent microscope, fixing the exposure time to 200 microseconds in order to optimize the time of flight of the particles within the microfluidic channel. A total number of 200 frames was used in order to have statistical relevance during the analysis. And of course, the acoustic waves were generated through a function generator coupled with a power amplifier, as you can see from this slide. Particle trajectories were then extracted and analyzed through ImageJ. Here you can see two frames, one for the reference trajectory obtained at 0 volt, and the second one for the maximum deflection obtained at 10 volts for particles of 20 micrometers for diameter and at a flow rate of 100 microliter per minute. What was done was basically extracting the reference trajectory and then use this trajectory to evaluate the lateral deflection at the different operating conditions. Then these values were averaged at least among 20 trajectories to have statistical relevance. Accordingly to the simulations, the largest particle deflection was observed around 19 micrometers at the lowest flow rate of 100 microliter per minute and highest input voltage of 10 volts. This condition proved to be the most effective operating point within the explored parameter space. Employing this condition in the experimental validation, we can see how the measured values for the lateral displacement are in very good agreement with the simulated values, and the discrepancy in percentage between two values is within the experimental uncertainty. So we can say that the model is working. In conclusion, we were able to build a fully coupled three-dimensional multi-physics numerical model able to predict the deflection of particles under the actuation of acoustic waves. The model in particular was able to capture the dependence of these trajectories on the size and driving voltage and flow rate. And the estimated values were in a very good quantitative agreement with the experimental values. In future, we would like to employ the same platform for different kind of particles geometries and solutions, but the end goal is to use this platform to improve the sorting efficiency in clinically relevant scenarios, such as CTC isolation from blood and sperm selection for assisted reproduction procedures. Thank you for your attention. If you have any question, I will be glad to answer you.